In today's lab on constant velocity, a rolling mini soda can was observed on a table. The can is known as a system while the surroundings include the table that the can was rolling on. These are the parameters of the soda can. Tracker was used to record the object in motion. In Tracker, only frames 13 to 29 were manipulated when the can was in motion in order to prevent the force of the push from my hand to create an extra force or there to be more acceleration as the can kept rolling. The point of mass and the origin were at the center of the soda can's base, with the x-axis being the direction of motion. The can rolled in the positive x direction. A question might be, does the orientation of the axis change the results if you were to flip the axes? Flipping the axes will allow the object to move in the positive, negative, x, y, or z axes. The object will still be moving at a constant velocity and there would be no change in the results. Let's see our object in motion. Tracker records the time and the position throughout all the frames that the can is in motion. Initial velocity was found using the first two time and positions that Tracker recorded. The values did not have to be the first 2 points, as they could have been any of the values, as long as they were calculated using the first step, because these would produce the same initial velocity. Initial velocity was found by calculating the change in position over the change in time, which was found to be 0.141 meters per second. The final velocity was then calculated by using Newton's second law and knowing the initial velocity and the final time shown by Tracker. The final velocity was found to be 0.141 meters per second. Knowing that in constant velocity, final velocity equals initial velocity as shown before, the final velocity was also found to be 0.141 meters per second. The experimental graph is shown to be linear and positive. A model graph was also created in VIDLE. By manipulating a Python file that was given in lab, a model graph was made. Ball.m is the mass of the can. This is shown in kilograms. The position is the initial position, which was also 0.002 meters. The initial velocity, which was found, is 0.141 meters per second. Other things that were unhashed was these lines in order to create a CSV file which would later be used in Google spreadsheet. The time step was kept to be 0.01. This is because the overall time in the whole lab was only a few seconds, and this allowed the time step to thoroughly calculate the correct velocity. The calculation loop is made by a while loop. The final time is put as everything falls under the final time. The net force is zero throughout. It is not possible to know which pushes and pulls gave the net force of 0. The different pushes and pulls cancel out to give the net force of 0. The can's final velocity is shown by creating Newton's second law, which is initial velocity plus the net force over the mass times the change in time. This is the updated position, which shows the final position of the object, which equals the initial position plus the initial velocity times the change in time. Knowing this, we can run our module. A model of the graph is shown along with the graph of the modeled experiment. By moving the CSV file into a Google spreadsheet, we create a position versus time graph of the model versus the experiment. The blue dotted line is the experiment line, while the straight red line is the model position. These two are clearly very similar as in they're linear and they both are very close to being positive. The experimental position is a bit shaky and a little farther away from the red line. This could be of possible changes in the slope or as well as acceleration or outward forces that cause the object to not move in constant velocity. Overall, this experiment was effective in showing Newton's second law and the momentum principle.